So to start the second unit of AP Physics 2, which is thermodynamics, we're going to look at just a basic understanding of what things are doing in a solid, liquid, and gas, specifically the particles. And really what we see is that particles are always in motion, right? So the particles, when they are in a solid, they are simply vibrating back and forth, but again, there's motion. When they're in a liquid, they're able to move past one another, so there's a little bit more motion in them, and then a gas, the particles are able to freely move throughout the volume that is available. But again, we're always in motion. Now, what we need to understand is that temperature is really the measurement of this motion. So temperature is a measurement of internal energy of an object due to the motion of the atoms or molecules within the object. This is the internal energy is known as thermal energy. And what we need to understand is that not all particles have the same kinetic energy or have the same internal energy, but the system is modeled on an average. For the sake that we're going to measure the average kinetic energy as 3/2 the Boltzmann constant times temperature in Kelvin. Right, so we have to remember that 1/2 mv squared is kinetic energy. And so what we can look at is the idea that what is the velocity of particles within a substance? Well, the velocity on average is going to equal 3 times the Boltzmann's constant times the temperature divided by my mass, square root. So my 1/2 goes away because the half here and the 3/2 here, the half on the bottom is going to cancel out. And so this is going to be my average velocity of the particles, right? So if we were to look at the idea of, and AP really likes this idea of, the number of particles and the velocity, right? So you might get a graph that looks like this, right? So this is really my average here. We're going to have some particles here that aren't moving or moving very slowly. We'll have some particles down here which are moving a lot faster, but this main area here is the average, right? So the area underneath the curve is kind of all the particles that are within my substance. Now, if we look at this, right, there is a direct relationship between the velocity and the temperature, right? So this doesn't mean that it's equal, but as the temperature goes up, the velocity of the particles goes up, right? Or as, you might say it the other way, as the velocity goes up, the temperature increases. And so what we could expect from this graph is that if the temperature rose, we would get a graph that looks more now like this, right? Where my graph is actually going to get a little bit lower because the particles have a little bit more spread out in terms of the variation of different temperatures or in different velocities. But my curve basically gets pushed further to the right where I have a higher average velocity. If I were to cool down, my graph might look something like this, right? Where I have a higher or a lower average velocity, but and a higher number of particles that are going to be within that. Another thing we can look at is the idea that if we have two different gases, so we'll have the similar graph, we might have a gas that looks like this. We might have a second graph that looks like this, right? And we can say that the temperature of the red equals the temperature of the blue. And what we can tell by this then, right, if this is the number of particles and this is my velocity, is that the mass of red and the mass of blue, right? So because they have the same temperature, their kinetic energies must be the same. So the kinetic energy of the red must equal the kinetic energy of the blue. Well, we know that kinetic energy is 1/2 mv squared. And so what we can see is if I have a larger velocity, I must have a smaller mass. And if I have a smaller velocity, I must have a larger mass. So we could see that because the blue has a smaller velocity, it must have a larger mass. And so the particle, maybe we're talking about a gas, right? Maybe this is, the blue is CO2 and the red is just oxygen, right? And that the mass of these objects, right, the mass of CO2 is greater than the mass of simply the oxygen or O2. And that would be, if these two gases are in the same temperature, they're maybe in the same container, the oxygen particles are going to be moving with a greater velocity than the CO2 particles because they have that smaller mass. Or excuse me, the velocity of the CO2 is going to be smaller because it has a greater mass. Now, again, with this, we could figure out, determine the average kinetic energy of molecules in a state cooked to 345 Kelvin. Again, the idea is our temperature needs to be in Kelvin. We can just plug in 345, use Boltzmann constant, and then we can figure out the average kinetic energy. So not a hard thing. A little notes here of just how you could convert between Kelvin, Celsius, and Fahrenheit. I don't ever see this as being necessary, but just making sure we understand. One thing to note is that Celsius and Kelvin have the same scale. So the change of temperature in Kelvin equals the change in temperature of Celsius. This is actually pretty valuable to know. Kelvin is just 273 degrees or 273 more than Celsius. But if I increase my temperature by 1 Kelvin, that is the same as increasing my temperature by 1 degree Celsius. So this is an important factor that's going to come into play as we move throughout the thermodynamics concept, where if we just need the change, whether it's Celsius or Kelvin, we don't have to convert it because we know, 30 degrees change in Celsius is equal to 30 change in Kelvin as well.